So in question 6, we've got a medical researcher studying the number of hours plotted along here, that a patient stays in hospital after an operation. We've got a histogram, and we're supposed to use the histogram to estimate the probability of being in the 10 to 30 hour region. So I've popped on our two limits that we want to find, and I've more clearly identified the areas involved. Let's now number those. So reading off the scale, we need to know the number of people trapped between the two yellow lines. So it'll be all of area 4, it'll be all of area 5, it will be half of area 6, and if you work it out, it'll be 2/5 of area 3. And there it is written down. Remember, the areas involved, of course, will be the height times the horizontal distance. If you work that lot out, you find that this comes to 48.4. So the probability of being within that region will be this number divided by the total number of patients, which is 90. And this turns out to be 0.538. And the answer to part A. So in part B, Thomas now suggests that T can be modelled, this distribution in other words, by a normal distribution. Well, just look at the shape of the histogram. This is nowhere near like a bell curve. So no, we can reject that suggestion straight away. So there it is written out. The distribution is not symmetrical and therefore not a normal distribution. And that will get you that 1 mark. Question C takes us more into pure mathematics than statistics. We've now got Yang suggesting that the histogram could be based on a curve, kx e to the minus x, where x is between 0 and 4, x being measured in tens of hours, which covers our original plot from 0 to 40 hours. Use algebraic integration to show this. So we're integrating from 0 to n, x e to the minus x. So we've got limits, so we don't have to bother with c, the constant of integration, but we have to integrate this. Well, this is integration by parts, and there's the formula. And in accordance with the use of that rule, we need u, when we form the second integral, to be simpler. So clearly I'm going to choose this as u and this as dv. So our integral becomes x, which is u, then we integrate dv, and this becomes minus e to the minus x, minus now the new integral, v again, which is minus e to the minus x, multiplied by du, which is 1. So this is equal to minus x e to the minus x. And if you work out the number of minuses, we get a single minus again, e to the minus x. And this is between the limits of 0 and n. And if you put those limits in, you indeed will get 1 minus n plus 1, e to the minus n. And that's the answer to part C. And in part D, we've been asked to show that this model produces an answer for k to be 99. So the answer we got for part C is the area under the curve from 0 to n. So if I wanted the area under the curve from 0 to 40, I would substitute n is equal to 4. And we know the real area under the curve is 90. So I get that 90, plugging these values into here, must be equal to k, multiplying by this area here, which is 1 minus, n remember is 4, so this is 5 e to the minus 4. And if you pop that lot into a calculator, you get that k is indeed equal to 99, which is the answer they wanted. So I've done some moving around. We've now been asked to estimate this same limit of the histogram between 10 and 30. We've been asked to using Thomas's model, which is a normal distribution, and then Yang's model of the exponential curve. So let's first of all get this one out of the way. Normal distribution, put all these in, and I get an answer of that the probability is 0.649, which is the first of the answers. And in part 2, we're now using Zian's model of y is equal to 99x e to the minus x. And from this model, we know that the frequency involved is the integral we worked out multiplied by our constant k. So I now need to sub n is equal to 1 and get a frequency 1, in other words, the number of people up to the 10 hours limit, and then I need to substitute n is equal to 3, which will be the frequency up to the 30 limit. Let's do n equals 1 first, and this turns out to be 26.2. Now with n is equal to 3, and this I get a result of 79.3. So therefore the total between 10 and 30 is equal to 53.1. So the probability of being within that limit by this model is equal to this number divided by 90, which is equal to 0.590. And that's the answer to part 2. And in part F, with literally no room left, we're asked to state one limitation of the model. Well, this is right back to the model, and we're only able to use x up to the limit of 4. So the model won't work when t is greater than 40. So I'll have to come up here and write the answer for D. So here I've said that t can't be greater than 40 hours because we're limited to x to be less than 4. And that should get you the 1 mark of that remaining part of the question.